All right, so let's continue. So we learned in the previous lecture, or the previous half of the lecture, how dynamic programming could be used from a top down, so-called memoization, meaning we are remembering or caching results which turn out to be useful. Like in Fibonacci, case Fibonacci, right? We don't have to do these recursive calls, right, over and over, right? We remember all of these, right? And again, it happens to work, right? The thing is, of course, so this is it's worth trying. If you have a recursive solution, it's worth trying. Just put some cache and see if it works, right? I mean, the thing is, sometimes the problems, even with recursive calls, maybe you don't make multiple calls, and then there's no need. Then this won't. There will be unique calls for each sub call. It will be unique, and then this caching will not help you at all, right? So let's go to our other approach, which will be bottom up, right? So we are going to start by building the simple solutions. Right? We start with, in this case, 1, right, or case 1 or case 2, and we are going to store the sub-solutions, right? So it is an iterative solution. It's called also tabulation. So in original paper, this is the only one, the Bellman, right, Richard Bellman, right, this guy here, right, he used the bottom-up approach. Again, he was not really using computers, he was just tabulating. He was basically making tables like, like Excel sheets, basically, right, with these solutions, basically, right? So, but we are going to do iterative solution Fibonacci, and I think again it seems very trivial, and again I'm showing you this simple solution again so you get the idea of this, right? So we're going to store all of them, right? So we start with 1 1, we need 2, right? That's our table. In this case it's not really a table, it's actually a list, it's an array, right? But okay, again let's pretend we don't know any formulas, we don't know anything, right? And so basically if it's less than 2, basically, right, off by 1 errors, maybe, right, 1 0, right, 1 2, right, maybe we should put 0 here first, maybe, right, maybe we can do this also, right, just to be sure, right, maybe, right, and then, or maybe this is enough actually, right, we don't need this actually, right, 0 1 would be fine, right, let's assume that the case 0 actually gives you 0, right, again, here we take the position that fib 0 is 0. Should be 0, right? But okay, that's off by 1 error. So again, sometimes you want the first 0 want to be 1, maybe, right? So, but again, it's not going to change the code, right? So we start with 2, right? We set the index to 2, and here we keep while we have not reached the end of the index, right? We keep adding we keep building our table. It's a one-dimensional table in this case, right? So we keep building up our answer table, right? Of course, it's not free, right? It's not free. Nothing in life is free. Here, right? We'll analyze this cost a little bit, right? And of course, we increase the index. Also, maybe we could also write this as a for loop. Looks like, right? We could write this as for loop, right? But again, I think this solution, you can see the idea, right? So we have an initial state, and we keep building up this solution space, right? So let's take a look what happens, right? So Fibonacci 2 will be 1, right? Fibonacci 4 will be now 3, right? 1 1 2, and Fibonacci 100. Yeah, it works. Yeah. So, and actually, of course, we have inside, right? We have these fibs, right? So basically, of course, we are very wasteful, right? We build up the solution space, this table, right? But we don't need the full table, right, to get solution, right? So we are wasting memory actually, in effect, right? And in this case, if it's Fibonacci, right, we have these huge numbers, right? And they actually get kind of expensive to store, right, at some point, right? You're having these big numbers, right? These big numbers with I don't know how many digits, right? And they keep getting bigger, right? And you don't need them, right? Then this is actually going to increase some serious memory space costs, right? So maybe not ON, maybe bigger, right? Actually, as far as memory, because remember, right? Big O complexity analysis, right? That there's also space complexity, right? For things we do, right? There's also space cost, right? So yeah. course, also notice this hash table, which is dictionary. In the case of Python, of course, has space on, right? You need n items. Well, obviously, you need to store n items, right? Seems such a simple idea, but yeah, of course, right? So always there is some space, incurred space cost, right, on top of everything else. So, so what's the complexity of the solution? Of course, this looks extremely linear, right? It looks like linear, assuming with a big assumption that this is linear as well. And I think it is, because of course depends on the list. Appending to the end of some data structure, generally amortized, meaning over time, should be, appending should be fixed cost, basically, right? You just find a place, right? It shouldn't matter whether you have 1 million items or 2 million, right? So you have n operations, right? This looks like an n operations, right? And this should be fixed cost. Of course, again, with the provision, this is for small numbers. Once you get to these big numbers, this appending might be actually some extra costs you might not expect. That's the thing. Like in theory, you look, okay, everything looks fine. But when you start working in practice with these big numbers, there's also this cost of manipulating huge numbers, right? So, of course, hopefully in real life you don't need to work with these such big numbers, right? So, but I hope everybody understands this solution, right? Table, or list in this case, right? That's what's called table in dynamic programming terms, and we build that. So easy, right? So if I give you a dynamic programming problem in midterm, you'll say, okay, yeah, no problem. I know this. Yeah, no problem. So, but let's time this, right? Fib is fast. We still have it. And I believe this will be slower, right? This should be slower, right? Because, why? Because we're storing these big numbers in the list, right? And this is basically what's really costing us. So, microseconds, but this is nanoseconds, so this is about 100 times slower, right? Not too bad, not terrible in this case, but yeah. So, how about 100? Because we're storing these bigger numbers, right? So still 21 microseconds. Again, still fast. It's 20 millionths of a second, right? Still usable, right? But again, unnecessary maybe, right? Again, I'm not going to do this. We can do it actually 8 milliseconds. Yeah, why not? Let's see if it's because we're storing huge Fibonacci numbers in our list, and of course, then what's happening is the program runs. And it's all thrown away. The garbage collector in Python throws away all this big data structure, right? It's all gone, right? At some point, right? So you don't need it anymore. Okay, right? So we'll check if it works. Of course, it should work. Right? 0, 1, 1, 2, 2, 3, 4. It works fine. Okay, great. All right. This is just playing around. We don't need to play around with it right now. So the basic idea, right? So let me put the text here. Improving. Optimizing, let's call it optimizing the tabulation solution. Do not store everything, right? Right, that's the basic idea. Yeah, that's the basic idea, right? And here it's trivial, right? Fibonacci, you again, like I said, you know this, right? So this is basically you just need two values, right? You don't need anything else, right? That's it, right? So. And again, I'll do 0 here, I guess technically to have base 0 again, fib 2, 0 would be 0, right? 0, right? And if it's 1 or 0, you know this, right? Previous and current, right? So, yeah, of course, again, now the names, previous, current, of course, this is the case where naming might be slightly confusing. So we're turning previous, or maybe let's do less than equal 1. Well, which one should we return now, actually? That's a good question. Right. Here now it's not so simple. Right now, of course, now I made this little tiny change, and I introduced a tiny error here, right? Because I don't have a list, right? So I would probably either need an if, or maybe I could put them in a tuple or something. Let me see here. Hopefully I could do two ifs, right? If case is, well, if since I'm lazy, right? Again, I'll do this shift alt error. Up arrow up. So 0 with previous, current, right? Of course, right? You could of course rewrite this with these are two base cases. We have our base cases, right? And now we have indexes 2, and again the same thing. Of course, again, this is Python specific optimization. In other language like C++, right, you could do this in such a nice way, right? You have to use a third variable, right? Here, we're doing a little trick, right? What's happening here, right? So we are creating a tuple, right? Python tuple, right? And instantly we are reassigning, right? Basically unpacking the tuple, right? So this becomes that, right? Previous current becomes current, and current becomes previous, right? But the reason this works and it's so concise, that's why it's nice in Python, because it's created, right? These values, right? It's right side first, right? In this case, right? So these are done first, right? This calculation, previous current and current, right? This tuple, right? It's actually a combined structure. Is created before, right? Before actually reassigning these current and previous values, right? So right side first and left side and reassign, right? Again, you couldn't do it if you want to do this separately, right? You have to use a temporary variable, right? Yeah, and even in Python, right? I couldn't just it would not work if I did this row by row, right? Previous, so current equals previous current, right? It wouldn't work, right? I can't split it in two rows. Then I need a third variable, right? So right side eval first. Again, this is language. If the language does not support it, right? If I can show you, maybe since okay, maybe a second. Yeah, klausos. Tas ir labi, man ir lekcija. Apkodās? Nomira? Baroklis, droši vien, jānomēr, baroklis nestrādā vai mārs platūrās. Es aptīšos. Jā. Es tev piezinu pēc vieniem, labi? Jā. Alright. Jā. Okay. Right. Now, so IT problems. Now, so we are at the. So you guys, this makes sense, right? You don't need to store more than two values, right? Yes. Yeah. Okay. Right. So this is like in this particular case again, we took the easiest problem. I don't know. Maybe somebody can figure out an easier problem to show as an example. This is about as easy as they come, right? So maybe we'll get something slightly harder, right? So Fibonacci works, version 2, and let's time it. So this should be a little bit faster, right? Let's see, 3 microseconds, and how much was that one? I believe it was 7. So about half the time. So yeah, so we shave off half the time by not using all this wasteful data structure, right? But of course, again, this is should be done only once you have working solution. Maybe for more complex problems, store extra data, right? Again, memory generally is cheap, right, and should be used, right? So again, but then afterwards, make it work, right? Make it right and make it fast. Yeah, that's what we should say, right? So make it work first, right? Then make it correctly, right? Optimize, and then you can optimize it afterwards, right? So, and again, 100. I think it also should be about half the speed of the full table solution. But again, in this case, caching, the built-in caching is faster, right? Again, so again and again, this overhead, again, this takeaway, one of the takeaways text, one of the takeaways from these tabulated solutions is that some extra cost is incurred by storing the huge even numbers for Fibonacci, right? So theories again sometimes not, often in theory it is assumed that large numbers they have same complexity, right? But it is not the case, right? Okay, yeah, okay. So let's go to other problem. This is again, I mentioned the Pascal's triangle, named after Blaise Pascal, the famous polymath from 17th century. But was he a gambler? Well, he wasn't a gambler. He was more, of course, philosopher. But he studied gambling, right? He studied, of course, combinations, right? And this is a Pascal's triangle, right? Of course, there's formulas for it too, but the idea is this: you start with 1 at the top, and you keep building it up, right? By summing up previous top to, like, your neighbors to the top, right? That's a formula, right? You've seen, I'm sure you've seen this before, and it happens to be that it has a combinatorial meaning, right? It's a number of k-sized subsets you can get from a size of k size n, right? So combination is what? A selection of items from a collection, but order of selection does not matter, right? So this is the thing, since I don't do combinatorics every day, right? I always forget which one is combination, which one is permutation, right? So combination, technically, in English at least, is a selection of items, but the order does not matter, right? If the order matters, then you get an extra. You get more, right? There's more of them, right? You need to multiply. Yes, the formula changes a little bit, right? So, okay, so. Basically you add another factorial basically on top of it basically. Okay, so let's start with a really bad solution again, but but the beauty again, the bad solutions, right? Okay, n and k, right? N is a number, is a size, is a row, right? And k is how many if you want, right? So you start at top, right? So basically, if k is 0 or n is 0, by it return 1, right? If n is 0, right? So if k is 0, right, return 1, right? And n is 0, right, return 0, right? It's completely empty. So n is the size of how many items you have. K is how many subsets you want. So k is again so k is how many. Is the size of the subset, and n is the size of the whole set, right? Okay. Now, and again, beauty, but of course you already know what the problem is, right? Beautiful solution, but it's gonna, how should I say, stink, right? It's gonna stink, but we can use it, right? So let's see, if you want 1, 2, 1, let's see if this works. Yeah, 1, 2, 1, beauty, right? 1, 3, 3, 1, looks good, right? Works, amazing, right? So it works. You can do 4, right? And you can see, like, I think I did a loop, right? So let's do a loop. Or for k in range 6, yeah. So I'm lazy, right? 1, 5, 10, 10, 5, 1, right? Remember, this was what we used in the beginning for the longest degree subsequence, right? You had one way of picking the subsequence of size 5, right? You only 1, right? 5, 5 is going to be 1, right? So then it goes down to 5, 10, 10, 5, 10. Okay, so this horrible solution, right? I could of course say, okay, this is great, but no, this is not good. We'll see why it's not so good, right? Because again, anytime you see 2 recursive calls in a same recursive, that's very dangerous. I mean, that is very, very suspicious, basically, right? Because you are potentially having this big exponential explosion, right? Potentially, right? If you don't take care, right? This is really, because it's such a simple solution, you make it work first, right? But let's go about making it right. So let's time it, and we can see 20. So 12, right? This order doesn't matter. How to pick 12? So how to pick 12 items? Order unimportant from size 20, right? 125970, right? So, and if I want to see, if I want to play lottery or something like what's pick 6 or something on the 45, I probably can't use this function because we already see this is pretty slow. Well, 0 seconds, not too bad. But 0 seconds doesn't tell us anything, right? Maybe it's, yeah. Well, actually, it took 2 seconds to run this cell, but here it means that each cell, right, 0 seconds, in this case, this is less than 0.5, right? So we, you know, it was a little bit misleading, right? 300 milliseconds, right? That's bad, right? That's bad. All right, so we already learned this. We learned this trick in the previous hour. You can use func tools, right? In fact, I don't have to import it, right? I'm not going to import because I already have it, right? So again, decorator. Again, we use this built-in decorator, a wrapper around our function, right? Yeah. So basically, what this little @ symbol does, basically, this is a function, basically, well, actually, you know, part of a bigger, right? So it adds the cache. We don't have to do it ourselves, right? So, and that's all. And that's all we have to do, and it should help, right? Again, because it's 3, right? And here you can see it very clearly, right? It grows pretty quickly. So let's see if this works. Actually, I don't know. Well, it looked good, right? It looked good. Again, lots of recursive calls, but it looks like something. Yeah, look at this, 130 nanoseconds. So this is almost like a, oh, that's million times speed up, right? 1 million times, right? But 3 million times speed up, 3 million times, right? Well, of course, again, because in here, if you see nanoseconds, it probably means it's already looking up solution. Basically, you know, it's just getting out of bed, right? Putting on pants, and then maybe getting coffee, right? And getting back into the bed, basically, right? So, because it has a solution already, right? So nothing to do here, right? So, again, very good. But let's see if we can do a bigger one. Let's do, yeah, I'll do bigger. It should still be pretty fast. Again, here, right? It's possible maybe the cache is already, you know, has the solution. But here, right? Right? This should also be, right? We don't really lose any speed basically here, right? And we can go bigger. So let's do lottery, right? Let's do lottery. Yeah, when I did this first, I didn't have this, right? I think this like version 3.7 or 3.6, I think, when I did this before. Let's see. Yeah, 1.5 seconds. Ah, right. This is a bad one, right? This is a bad one. This is a bad. Yeah. This is a bad one, right? 1.5 seconds, right? Horrible, right? Yeah. Okay. So one more time, right? So yeah. So this is a cacher, right? So CMM, right? So we can, for example, do things like we'll use them in Python 3.10, right? So. Right, LRO caches we've been using, right? So this will, right? So this is 8 Queen's problem. So we need 4. We'll look at Queen's problem next lecture, right? 3, that's 4 billion ways of picking 8 queens, putting on a chessboard, right? How about lottery? I think I did lottery, right? Yeah, there's no lottery. Yeah, we already did this, right? So let's see lottery. How about lottery? I don't play lottery, but what are how many? 6 pick 6 out of 50 or something? What is it all? Anyone plays lottery? No. Good for you guys. No. I mean, theoretically, mathematically, of course, if it's a progressive lottery, it makes sense to play at a certain point, right? If it grows, right? It's actually advantageous at some point, right? If you're patient, like once a year, once every couple of years, it might make sense mathematically, statistically, right? Probabilistically to play lottery, right? If it's like so. But okay, but let's say, I don't know, it's 6 pick 6 or 50 or something like that. Okay, let's do lottery example. I don't know. Let's take, I don't even want to look at the gambling sites, but let's do this. Lottery example, lottery example, right? Let's say lottery pick 6 out of, I don't know, 51 or something. They usually put some weird numbers. I don't know. All right. Okay, so what are our odds, right? Again, order doesn't matter, right? The order of the balls they take out of the jar doesn't matter, right? So it's going to be C mem. So first the number is 50, yeah, 51, 61. Okay, perfect. Okay, AI knows what I'm doing. Yeah, right? Okay. So what are my odds? Well, that seems very easy. Only 18 million, right? So like, not too bad, right? If it's almost, I think they usually do like 7, that's why they do 7, they get extra, they add a little extra complexity, it's still easy to calculate, right? So picking up, so 18 million, so more than 18 million, right? Winner. Not too bad, I guess, but still. Right, usually they actually divorce. They have exactly like the 7th one, right? So they add 7th by adding 7s for now. The odds go down, right? C mem, yeah. Okay, that's what they do usually, right? Now it looks like more like it, 115 million odds, right? Right? So you need to buy it on app. Well, theoretically, right? You know about this, right? They have these. It's been done before a couple times, and there's this progressive lottery, right? At a certain point, if the money is enough money, people actually made these pools, and they bought all combinations, basically, right? Guaranteeing a win. But this is dangerous, of course, right? Why? Because somebody else might win as well, right? And then you have to split the prize. And if there's like, usually happens in these progressive lotteries, at some point the prize is so big, everybody starts playing, right? And then you have like 6 winners, right? So it's not, it probabilistically made sense, but since there's so many people playing, and of course taxes and so on, maybe you might break even, maybe, right? So there's been a couple of cases, and sometimes, anyways, lots of stories about this. But yeah, it's possible, right? It's possible. But okay. Now, yeah, we already saw these recursion errors, right? And we don't want to do this, right? So, again, we saw how adding cache, right? It is just easy win, right? We got the basically perfect, almost perfect function, right? Again, with the downside, of course, recursive calls, you have possibly some stack limit, something like that, right? So let's make this iterative, right? So, right, you don't have a problem with stack anymore, right? Iterative, right, this has special cache, right? But we can use maybe no multi-dimensional array here, right? So maybe do a lower level in lower language like C++, right? We can make a cache, right? Right. So iterative will start in the beginning, right? So let's do it, right? So what we'll do is we'll use a dictionary. In this case, we'll use default dictionary, right? You can use regular dictionaries. They're the same basically, but it has a pretty much all languages have hash map type of dictionaries, right? Map, hash map, and so on, right? Unordered map in C++. This will be in a couple of weeks. We'll look at the unordered map in C++, right? So we'll use that. So Pascal up. So we initialize it, and also, right? Basically, we also tell it what's going to be integers, and actually, I think it gives you 0, right? Default dictionary. If you look for, I think, if I remember correctly, default dictionary. If you don't have anything, you get 0, I think, if I remember correctly. Right. So, let's look at this function. So basically, we look k out of n, right? For row in range n, right? We are going to build up, basically. Start with 0, right? And we go up to n, basically. Right? So we are going to build a solution. So we start with 1, right? Very beginning, we start with 1, right? And of course, let's go back to let me add iterative Pascal. So let me add the text. Pascal triangle. I'll show you the Pascal, Pedro Pascal, right? So no relation to mathematician, I don't think. So okay, yeah. So the problem is, of course, it's not the structure kind of funny looking, right? Because, all right, how do you actually, well, also use dictionary basically, right? So this is, 1, I guess. This is 1, 2, 1, 2, 3, 1, 2, 3, 4, right? It's kind of like keeps increasing, right? A little bit. So again, and you have a real-time problem, right, it might be hard to figure out the exact structure what you're going to store, right? So here again, it's not just a simple two-dimensional table, right, but something like that, basically. So, right, so again, this is a dictionary, right? So again, this part here we are using a tuple, right? Technically, right? Again, if you again, note row. This row is we are using a tuple as key, tuple of two numbers as key. Or dictionary, right? So this is not technically not a table; it's dictionary. Well, again, so we don't store any unnecessary values. So let's use this. So for column in range, right? Right. So if you think about it, how we are building up, right? Why should this work, right? So because you might have some questions, maybe. We only add the first column, 1. Why don't we put the 1 at the on the right side? Well, let's think about it, right? We started the first solution, right? What will happen is, notice this part here, the magic is here, right? 0, 0, right? So, if you remember your dictionaries from Python, get as default value, right? We said the default 0. So, if there's no entry, this means we are out of bounds of our table, right? So it will work beautifully because you either have 1 at top in the beginning, right, or have nothing, 0. So we'll be able to fill out our table. It will work perfectly, right? So because we know the edge always has 1, right? It will naturally fill out, basically, right? So if you want, I can add a debugging for you. So you can see this. I'll add debug. Debug equals false, right? This is just a flag, right? I mean, I could say or verbose or whatever, right? And I can do this if debug, yeah, print sit not sit row call, right? Okay. And of course, since row, right? And name is nothing, right? Right? Yeah, here, right? In a loop, if debug, what I do is just print nothing. Yeah. Okay. Right. Or maybe comma. And yeah, comma, I guess, comma. Yeah. All right, let's do this. Okay, let's see what happens. Let's see if I made a mistake here. No, I don't see. So we have 2 loops, right? So again, you can think of complexity. You see 2 loops. Well, this looks like me n times k, right? N and k, right? And these are all fixed. These are all fixed costs, right? Get these are all O1 operations. Again, you have to be careful in some language. Maybe this dictionary could be log n operation, right? And you have slower performance, right? Depends on the dictionary, right? Again, O1, right? So let's take a look. Okay, so do we want to make this? I guess let's try this, right? Let's do this. Return CNK, right? Let's build up. Let's see what happens when we build the solution. I don't know. Are we ready for this type of? This is going to be big numbers. Okay, let's try this. I don't know what's going to happen. No, it worked fine. Okay, you can see what's happened, right? You see, 1, 2, 1. But the thing is, right? So it's interesting, we're missing the first one, right? Sort of, right? At the moment. But I think because we skipped what happened. Oh, because this part here, yes, okay, yeah. We basically didn't print it, right? So if debug, and of course, come on, AI, yep, of course. Okay, one more time. All right, and now you can see what's happening, right? We have a bunch of zeros, right? Technically, right? We had nothing here, right? And eventually we fill out, right? And eventually get to 12, 12, 125, 970, right? We got to this part here, and we got the solution, right? Okay, do you guys, so you see what's happening, right? So we build up solution from these. Okay, this works great, and we're almost finished. So what improvement could we make this? If you actually need to calculate this value, right, somewhere, right? So what's the next way to improve this is, what could we do?
Maybe not store all of
Yeah, of course. Yeah, we don't, so, remember, we don't need to store all this, we don't need this, if we actually just calculate one specific value, right? We don't need this full Pascal's triangle, right? You could save a lot of memory by basically just need the previous row, right? That's it, right? Because the next values are only dependent, right, of previous row, right? This 2 depends on these 2 1s, right? This 6 is dependent on these 2 3s. It doesn't care about the previous values at all, just the previous row, right? So this would be improvement, right? Let's see if you can, I don't know if I made it or did I make it, right? So, yes, only previous row, I don't know. Actually, this will be something, we don't have that much time. So to do next, somebody can do it, or to do, I'll add myself. I could do add. Okay, well, let's see if AI can do it for me, right? Since I'm lazy, right? I need basically just be a little bit careful. Let's do this. So code, yeah, generate this. So let's create an iterative function that returns combination for k out of n using iterative table bottom up solution that only stores previous row. Okay, let's see if AI is good enough. I'm not really great on Gemini, right? Because, let's see, optimized. Okay, nice docstring, I like that. Okay, that's good to see. Okay, if k, okay, that's good. So previous row, right, that's all it is, right? So current row, so we have 2 rows, and so using list, again, we're using lists here, right? And also it's optimized, right? So previous row, this is only done once, right? That's only done once, right? Previous row is once, right? And so you start building it up, right? K, right? Seems a little bit wasteful, maybe, I'm not 100% sure, right? But let's take a look, right? Does it work? And what was it? What do they call it? Combination? Okay. So, was it 2012, right? Does it work? Nope. It's not defined because I didn't run it, right? Of course, right? Use code is caution. You might get dragons, right? 1. Looks like a fail to me. Looks like it failed to me. So, k. I think it has to be 12. It's reverse, right? It's yeah, nk with 12 out of k. Let's try one more time. No, it's worse than that. Okay, so it doesn't work. That's the problem with generative AI. That's 0 and 5 out of 3. So there is some bugs. Yeah, 1. Right. So it looks like here. Let's look at this. What the problem is. Right. So we had the previous row. Yeah, k. Yeah, looks okay. We can live with this for range. Current row 1. Yeah, that looks good. Append. Previous row, right. Append 1 at its end, right? That looks okay too, right? It looks decent, right? And then we switch, right? And once we have this previous row, we return k. This looks really okay, but there is some error somewhere, right? We probably need to add debugging here to see what's going on, what's the problem is. Again, or debugger. Of course, you can also use debugger for it, but I'll use printf, right? I'll use debug, right? And maybe you can spot the error already. So this again, I'm sure, again, remember, on midterm, you can use AI assistance, but it's not guaranteed to be correct, right? So you'll need to follow your ideas. So this, okay. Is this the problem? No, this looks okay, because k has to be at, less, well, I would say equal to, right? You can do equal, that's 1, right? Oh no, okay, here, yeah. Yeah, no, it's fine. Yeah, this is case 1. Yeah, okay, these look okay. These restrictions look fine. So where is the problem? Why are we getting zeros here? Okay, no, zeros because it's, okay, so this one here, why are we getting ones? There's something not happening here. So, J minus 1 plus J. And what's interesting is actually, I'm kind of curious, why does this work? Why are we not getting, right, that's why I would use dictionary. That's why dictionaries are easier, default dictionaries. Here with arrays, right, the tables is a little bit trickier, right? Okay, I had debug, right? And let's do this. Print if debug, print current row. Okay. Row, I'll do row. What do you call it? Row. What's the row? I, right? I. Okay, row I. Okay, yeah. Okay. Okay. Let's do this one more time. Let's see where the error is. So let's do 3, 5. Debug, right? True, right? Let's say false. False. Let's do false here. Yeah. Again, so I don't break the pre-existing code. Wait, 1, 2, 2, 1 looks.
Because it returns the last index.
Yeah, K. But the K is 1, 2, and 3, right? And but okay, but why does it return 1? Previous, wait. Return previous row is current row here, right? And K, yeah.
It returns the one, the rightmost one in the.
Looks like it, right? Let's see. Yeah, which is 1, right? By definition, right? This, I think this part here is the problem, right? But we saw I have a feeling this. Yeah, this should not be even added, right? So yeah, so you see the problem here, right? I see the problem is here. It's not a Pascal's triangle, right? This is you put them all in the same size. That's another problem, right? So yeah, it's almost works, right? But you see the problem, right? It's using the logic is okay, but the storage is not increasing, right? So you have this weird. So 5 is 1, 4, right? 11 is 4, 7, right? And these ones are mechanical, right? So this I would rewrite. It's easier for me to rewrite this as a dictionary, right, than a table, because you have off by 1 errors here, right? You might be again getting non-existing value. You'll have an index error probably, right? You have to check, right? So this is to rewrite. So I'll do fix me. Rewrite using dictionary, right? On we have increasing row sizes, right? Of course. Okay. So this is not working correctly. Okay. But let's you guys want to take a break. So you can read up about how to increase this large, longest increasing subsequence, right? You get caching, right? And this actually will work pretty well. So again, you have a recursive solution, you can use caching. So let's go into let's review this. So top down, you create a recursive solution, memorize it, and that's it, cache it, right? Bottom up, this is much harder in some problems, right? You have to figure out a way to store results, right? You tabulate, calculate up, right? Increasingly more complex results, more complex solutions, right? So, and of course, possibly, you'll need to store all the results. You can keep moving up, right? Again, you don't need all the rows of data. And again, where the difficulty is, that here today we saw a simple Fibonacci one-dimensional this table of solutions. For the Pascal's triangle, it only got difficult because we had a table, but it's sort of like two-dimensional. It's more like a, increasing table size, right? Two-dimensional, basically. But a more difficult problem might have multiple, right? You have a maybe three-dimensional, four-dimensional table, or maybe something bigger, right? So what you're storing, right? And it might be hard to figure out where to go from one step to another step. We'll practice maybe later on with some other solutions before the midterm. So we'd expect to have something like this, right? But again, you start with this brute force solution and see if there's something you can store as a sort of like result. That's basically your takeaway from today's lecture. Let's take a break till 11:15, and we'll have a break.